a second category of what's called regeneration or feedwater heaters in order to improve the thermal efficiency of a steam power plant cycle is called a closed feedwater heater. Now, I'm not aware that you're going to be assigned a problem like this in this class, but for completeness, it's important for you to understand, well, how would I analyze a closed feedwater heater? How is it different than an open feedwater heater that you probably will have had an assigned problem associated with? And so this section is called closed feedwater heaters. Let's look at how they're different from open feedwater heaters, and then the basics of how would you analyze a closed feedwater heater if you're adding that into your power plant system. Of course, you know by heart the four components of a basic Rankine cycle. And what we're looking to do typically is how would we improve the thermal efficiency of that? And one way is to add a closed feedwater heater in which we'll take some extraction steam from the turbine and use it to heat the feed water somewhere along in this line, not sure, but before it goes to the boiler. And so, yeah, why would we do this? Why would we add a feed water heater in the line? And so if you sort of study this temperature entropy diagram, you'll see that by raising this state 4 going into the steam generator, what you're doing is you're reducing the irreversibility of the boiler, of where it transfers heat across a finite delta T. And so do you see that the irreversibility rate is the highest early in the boiler, early in this process where you're putting in compressed liquid that's well below the boiling point at the pressure of the boiler. And so that would represent a source of irreversibility, heat transfer across a finite delta T. So the higher you can get this supply temperature, the more efficient your cycle will be. So what's the basics of a closed feed water heater? Well, a closed feed water heater is basically simply a shell and tube heat exchanger, very generic one I've shown here. And so in particular, recognize that the hot stream and the cold stream, both H2O, phase change substances, they do not mix with each other. They're kept separate from each other. That's the difference between the closed feed water heater and the open feed water heater. So based on the sketch, state 8, that's what would be coming into, that would be the feed water coming into the heater. There will be extraction steam. It's coming into thermal contact with the extraction steam that's condensing. So it's going to get warmer and warmer and warmer. And so it will be heated up to state 9, where it goes off to either the boiler or the feed water pump, depending on where this is going to be located. Probably will be before the feed water pump and after the open feed water heater. That's probably where it will be. And so on the heating side, we've got extraction steam from the steam turbine, and it is coming in the shell side of the exchanger. So it's exchanging heat with the feed water. And so it's condensing. It's condensing at constant pressure down to saturated liquid at state 12, where off it goes to be handled as condensate somewhere else. What would your sketch look like? Well, here's what your sketch would look like. I'm trying to move my picture around. I think that can work. Okay. Your simple sketch would look like a basic two-pipe shell and tube heat exchanger in which you've got the feed water or the condensate straight shot 8 to 9 on the tube side, and then you're showing on the shell side the extraction steam coming in basically as superheated vapor, or in some cases can be saturated vapor coming into the heat exchanger and leaving as saturated liquid out the bottom of the shell to be handled somewhere else. What else can we say? Well, we've got steady state, steady flow on both sides of the exchanger. we've got no change in kinetic or potential energy that we're going to worry about on either side. And so certainly you see that m dot 8 equals m dot 9, steady state, steady flow, one inlet, one outlet. And also our model is going to be that P8 equals P9. It's going to be a constant pressure process, and no work is involved, is it? We don't see a weight being lifted. We don't see a shaft coming out. So on the steam side, we've got m dot 11 equals m dot 12. And it also is a constant pressure process. P11 equals P12. And so I've just tried to number this in a generic way so you can see how would you set this up? How would you set this analysis up? Both streams, constant pressure process. Let's talk about physical limitations before we go and do the first law analysis on this. If you study on this and think about what you know about the second law, do you see that there's no way that you can heat T9, the feedwater temperature, you can't get it hotter than T11. No way, right? And so here is a second law limitation on what's coming out of the feedwater heater. T9 is less than T11, all right? Another physical limitation is that we cannot allow this water to be boiled. In other words, T9 has got to be below the saturation temperature. It can't be it can't be saturated liquid at P8 equals P9. So that's something as an engineer you've got to verify. You can't have any boiling here because it's got to go into the feedwater pump, and it's got to be incompressible liquid. It needs to be a compressed liquid going into a pump whenever it's pumped. We can't pump mixtures of vapor and liquid. Okay, another one. Let's see, what else do we have? We've got extraction steam coming in on the outlet side. Do you see that this temperature, so this temperature T12, the temperature of the condensate T12 has got to be a bigger number. It's got to be hotter than TH. There's no, so you can't cool your condensing steam down below the temperature of the feed water coming in. So T12 is greater than T8. That is a second law limitation. Okay. And so what, as an engineer, what does that tell you? It tells you that you need to select the extraction steam pressure. So you have to be careful on the extraction steam pressure so that the TG, in other words, T12, TG at P12 has got to be greater than T8. So do be aware of that. That's what guides the engineer in selecting the extraction steam pressure needed for the feed water heating. Okay, so that's an important point to make. So select your pressure, select your extraction steam pressure so that the saturation temperature, TG or T12, has got to be greater than T8 to get your money's worth. So what is extraction steam anyway? So extraction steam is coming from the turbine. This is a good cutaway view of an old school traditional steam turbine with a high pressure turbine section. Once the steam expands through those first three rows of blades, that's where we're able to, and then the steam continues to go into the medium or lower pressure stages. This is where we can extract through a valve. We can extract steam from the turbine to go to our closed feedwater heater. Same idea as the open feedwater heater. We're using extraction steam from the turbine to preheat the feedwater. And so let's see that turbine, there's your extraction point, state 11, and then this point right here is the exhaust from the lower pressure sections of the turbine going to the condenser. So what will the TS diagram look like for this closed feedwater heater? So it's more complex than the basic Rankine cycle. Let's see, 1 to 11 to 2. Well, that's going to be the turbine process, okay? In this case, it's shown as reversible and adiabatic, but the extraction point, some intermediate pressure between 1 and 2, P11, that's going to be where we're extracting the steam. And then what's that steam going to look like when it goes through its heating process? Our little sketch over here of what we're trying to analyze, it's going from superheated or sometimes saturated vapor down to saturated liquid, 11 to 12. Okay. let's look at the feed water side of the heat exchanger. Where, let's see, we're coming in, we're going to pump up our condenser outlet up to P8 so that we can pump it up later to the feed water pump. And so I'm pumping up the pressure to P8, which is going to equal P9. Then I'm going to go into my closed feed water heater. So this 8 to 9 process in the compressed liquid phase, that represents the closed feed water heater process, heating the feed water. And so on the TS diagram, you have a visualization of what's going on with the heating steam and what's going on with the feed water. A lot of students have trouble grasping that, but it's sort of important to understand what do our states look like on the TS diagram. Now we'll apply the first law. So we're trying to crunch numbers on, let's say, what will be our outlet temperature. So if we know the mass flows, let's say we know as engineers, we know the mass flow rate needed for our feed water. And let's say we have selected the number of pounds per hour of extraction steam we have available to us. Let's say that m.11 is known. Okay. Let's write the first law for our closed feed water heater. That'll be 2 inlets and 2 outlets, steady state, steady flow. No heat transfer from the casing or the surface of the heat exchanger to the surroundings. So heat transfer for that open system, 2 inlets, 2 outlets, is 0. And also, we're not lifting a weight. So left-hand side of the first law, Q dot in, 0, minus W dot out, 0. So 0 equals the sum of the m dots leaving minus the sum of the m dots in, HN. I didn't say that right, did I? M dot leaving, H leaving, sum minus sum of the m dot in, HN. So let's see, we'll study our sketch. Can't do this without a sketch. M dot H, 8 times H9 minus 8, out minus N, plus m dot 11 times H12 minus H11, out minus N. Pretty simple. You can do that in your head now, I hope. And so if we collect those terms, we'll see that on the left-hand side, we've got m dot H. I keep saying H. M dot 8, H9 minus H8 exactly equals m dot 11. That's the steam flow. H11 minus H12. Simple energy balance, first law, steady state, steady flow. And say, okay, well, what about number crunching? Well, let's see, usually H12, you're going to know your pressure. You're going to know the pressure of the extraction steam. And so H12 will be a quick lookup, won't it? It's going to be H sub F at P12 since it's a saturated liquid. That's why you don't need to go to the temperature table. You know the pressure, P12, and you know that it is a saturated liquid. That's how come you can go to the pressure table. Okay, and so basic energy balance for a shell and tube heat exchanger. And then you're going to solve for H9 and check back for physical limitations. Does it make sense to what I've designed? Does that make sense? Am I keeping H9 below the boiling point at P9? And then finally, the dilemma of what do I do with this condensate? That's a topic for a later time. 2 options. One, the condensate from the extraction steam can either go back to the open feed water heater, or we can take and we can pump ahead with yet another separate pump, smaller pump. We can pump that ahead in towards the feed water pump inlet. And so remember, a closed feed water heater is just basically a shell and tube heat exchanger. And so if you're interested in more background on heat exchangers, I've got a little video on Chapter 4, Part 10. So on my Chapter Key Points playlist, go back to Chapter 4, Part 10, and you can look at some more technical details about shell and tube heat exchangers. Okay, just recognize it. It's basically steady state, steady flow, 2 inlets and 2 outlets. Okay, just so for completeness. So even though you're probably not going to have any homework problems on the closed feed water heater, it's certainly important to know how would I analyze that once I get out into the operational world, or if you take some more advanced classes in power generation or thermal energy systems.